In this lab, we're going to practice writing methods, and we're going to learn about how software engineers measure the speed of an algorithm. When we build solutions, often there are multiple algorithms that solve the same problem. We need some way of comparing these solutions to determine which one is best. One definition of best would be runs fastest, but it turns out that the definition of speed isn't straightforward. One way we can measure speed is with empirical runtime. This is how long it takes an algorithm to run on a specific set of data on a specific machine. We measure empirical runtime with programs called benchmarks, and we can use empirical runtime to compare machines by running the same algorithm on two different machines. Or we can use empirical runtime to compare how two different algorithms run on one physical machine. The downside to empirical runtime is that the conclusions are always specific to how things run on particular physical machines. Since we live in a world where our physical machines get more power all the time, these kinds of measures aren't really good for comparing algorithms in general. In order to get away from depending on a physical machine for our comparisons, software engineers use theoretical runtime to make these comparisons. Essentially, theoretical runtime estimates the number of instructions the machine will execute as a function of the size of the input. Almost always, we only care about runtime when the input is large. For example, say we're searching for something in an array. If the array is small, the difference in runtime of two strategies isn't going to matter. With a small array, both will run fast enough. However, as the array grows larger, there's a chance that one strategy may be much faster than the other. To see how we measure theoretical runtime, let's play with this code and see what it does when the array x is in random order. This method uses our standard walking through the array loop, except that it stops one position before the end of the array. Let's remember that oddity and see if we can explain why it is that way after we study what happens in the loop. Inside the loop, the if is comparing the values of two adjacent positions of the array. When INX is 0, it will compare positions 0 and 1. When INX is 1, it will compare positions 1 and 2, and so on. The comparison it is making is checking whether the thing in the INX position is bigger than the thing to the right of it. In other words, it's checking to see if these two positions are out of order compared to how we want them to be sorted. At this point, we can explain why the loop had to end one step early. If we had let INX become the index of the last position of the array, the indexing by INX plus 1 would have caused an array out of bounds exception.
To summarize, at this point, we know this loop is walking through the array, and at each position, if that position is out of order with the position to its right, we do the stuff inside the if statement.
So then the question is, what do these three statements inside of the if statement do? Let's look at them in detail. So let's be the machine, assuming that x has this data in it, and that INX is currently 1. In that case, the comparison will check if the 42 is out of order with the 3. It is, so we will go into the then block. That code declares a variable t and copies the value in x sub INX into it. That will make t be 42. Then it copies the value in x sub INX plus 1 into x sub INX. That will copy the 3 into x sub 1. Then it copies the value saved into t into x sub INX plus 1. That will put the 42 into x sub 2. The effect of these three lines of code is that the values in position INX and position INX plus 1 have been swapped.
As an analogy to justify this code, imagine you had tea in one mug and coffee in another. If you wanted to swap which mug was holding which drink, you'd need a third mug to make the swap. You'd pour one mug into the spare, pour the second mug into the first, and then pour the drink in the spare cup into the second mug. That's exactly what this code is doing.
This is a visualization of an array. The height of the vertical bars is proportional to the value in that position of the array. The pink bars show which values the algorithm is comparing. It starts at the beginning of the array. These two positions are out of order, so we're going to watch it do the swap. Then the loop moves to the next two positions in the array. They're in order, so it's not going to swap them, and it continues from there. Anytime the two things that it's comparing are out of order, you'll see it do the swap. If they are already in order, they'll stay right where they are. As this runs, each value is moved to the right until a bigger value is found. In the end, the biggest value was in the last position. Let's watch again with the biggest value starting all the way to the left to see if it always ends up at the end of the array. Yes, it does. So one time through that method, you're sure that the biggest value is always in the last position of the array. In order to find the theoretical runtime of an algorithm, we start by finding the operation that happens most often. Counting how many times that happens will give us our runtime. In this loop, the comparison is the thing that happens most often. It happens every time you go into the loop, and one more time when you realize that the loop is ending. If our array contained n elements, we will go into the loop n minus 1 times. So the number of times we execute this comparison is n times. When we talk about theoretical runtime, we describe it with a notation that is called big O notation. Since the thing that happens in play 1 most happens n times, we say that the runtime is big O of n. That means that the runtime is no worse than a constant multiplier of n. Here's a graph of what big O of n means. N is our x-axis, and runtime is our y-axis. Any constant times n is a line starting at 0 and increasing. Saying that our runtime is big O of n means that it is less than or equal to that line. The red area is where our runtime can be. So as n gets bigger, our runtime can get proportionally bigger too. In this method, if the size of the input, the size of the array, is n, the thing that happens most often happens n times. So the runtime of this method is big O of n. These two graphs show why we worry about runtime as n gets large. When an algorithm is big O of n, its runtime is growing linearly with the size of the input. However, if an algorithm is big O of n squared, its runtime will grow like a parabola. When n is little, it might win, but as n grows larger, that parabola grows at a much faster rate than the line grew. Given a choice, we'd take an algorithm that is big O of n over one that is big O of n squared any time. We generally only care about runtime for big inputs. If the input is small, everything will run fast enough, and there will be very little measurable difference between machines or algorithms. There are two ways that we can talk about runtime. Empirical runtime is measured by watching the algorithm run, and it is generally used to compare two machines. Theoretical runtime analyzes how the runtime will grow as the size of the input gets larger, and is generally used to compare algorithms. Theoretical runtime is found by finding the statement that happens most often, and then figuring out how many times it runs when the input is of size n. Big O notation is used to describe the theoretical runtime. When we say that the runtime is big O of f of n, we're saying that the runtime is no worse than f of n. So we're essentially bounding how much runtime can grow as the size of the input grows.